Hi, welcome to the lecture Data Visualization. This is part of the module Data Science in Julia. Throughout this course, we are implementing various machine learning models from the foundation level in Julia. And at the current level, we are exploring various concepts within data science. So this entire lecture will be dedicated to very simple data visualization techniques, which if you are familiar with, by the time you are implementing machine learning models and trying to communicate the results with someone, you'll be well equipped to do that in a highly visual, highly engaging manner. So let's start the data visualization lecture. So I have divided this lecture into a few different parts. So first, I'll do a brief intro into data visualization, especially through the basic packages like plots.jl. It's a very famous plotting package within Julia. And there are many different plot types which you are already probably familiar with. Line charts, scatter plots, bar plots, pie diagrams, and more advanced plottings like contour plotting or 3D plots, etc. So we'll explore all of that one by one, and the data will be created by ourselves for the purpose of showing during the plotting. But at the end of the lecture, we'll also try to visualize a real data from an actual data science project. So that will be the part 5. And at the end of it, we can also try to understand a little bit about customizing the plots, like how can we make the aesthetics of these plots slightly better by modifying few parameters. So with that, let's get into today's lecture. So as usual, what we are going to do is first looking at the packages that are relevant. So in this particular case, the package where we'll mostly spend our time will be plots.jl. That is the primary focus of our lecture. But I also want to let you know that there are other packages like Makey.jl or Veglite.jl, etc. So all of these are amazing packages. I have used Makey.jl and plots.jl myself. The other two, I have not used that often. Oh, actually, there is a minor typo. This is Vega Lite, not Vega. And the other one is Gadfly. So let's start with installation. So what I have done here is I have added some code snippets. So first I will walk you through the code and then we will implement it ourselves. So first is adding the plots package. So once we open Julia, we can do this in the Julia REPL as we have been doing in the past lectures. But otherwise, we can also do this in Jupyter Notebook. So we'll be first adding the package using PKG. First, we open the PKG, then pkg.add plots, and then using plots, right? Using plots means that's when you add that particular plots.jl library into your particular notebook. So let me open terminal. And then here, I think I'm already running a Jupyter Notebook. So I'll close that so that I can start from scratch. Terminal, let me zoom in a little bit, and then here I'll type Jupyter Notebook. So you should have Jupyter Notebook and Julia installed. If you don't know how to do this, just go back to our very first lecture in this playlist. So Jupyter Notebook will be opened as a local host on my Chrome, and here we can open Jupyter Lab. So click View, and I have Jupyter Lab. So open Jupyter Lab, and I have some things open here. I'll close all of that, then File, New, Julia file. So here, this is a Julia file. And if you want to rename, just right click, rename Julia file. Oh, actually, let me do this. Let me close everything and click the notebook here instead of the Julia file, Julia 1.1.1. So then it opens as a notebook like this, and I can right click on this title and where is my renaming? Yeah, rename notebook. And here I'll just simply write data visualization. IPy notebook is not needed. So data visualization in Julia. So first, what did we do? We had to add the package. So write using pkg, then pkg.add. Let me zoom in a little bit so that you can see better. I just want to make some room, so I close this part. Okay, pkg.add plots. So you have to put this in double quotes, otherwise it will not work syntax wise. and then using plots. Then we can run this. I'm pretty sure I have already installed plots library, so this should not take too much time for me while I'm running. But if you are doing this for the first time, it may take you some time. So so it's getting updated here. So this is what I said. You don't have to open in terminal. You can run it here itself. Otherwise, what you can do is you can open terminal, go to REPL, Julia, read, evaluate, print loop, evaluate or execute, I don't remember, but Julia REPL, you can run there. But basically right now the plots has been added, right? So this is the first step that we discussed in our notebook here. So we have finished adding the plots package. So now what we can do is we can plot a simple y equal to x square graph. So basically y equal to x square should look like this, right? Fairly straightforward graph, something like this. But when we are plotting something, it should have something called ticks. So these are called ticks. These are x-axis ticks and these are y-axis ticks. We can determine the frequency of these ticks. Then there is x-axis label. So we will write something here. There is y-axis label. Sometimes the plots will have something called legends, which is if you have multiple plots describing what is this one, if this is, let's say, dotted plot, right? Sometimes you could have two types of plots, and then you describe what is this and you describe what is the continuous line. So these are called legends. So there are certain parameters that you need to be aware of. So in this basic plotting example, you're first defining the range of x values. So x is ranging from 1 to 10. We can change this. And you're defining y equal to x dot raised to 2. Dot raised to 2 means here x is a range of values. It's not a single value. When you say x dot raised to 2, y will be every single value of x raised to 2. And then you are defining the plot simply by saying plot. Then you are defining the variable x and y, title, x label, y label, and then the entire graph label. So we can do all of this. So what I'm going to do today is, instead of making different notebooks for different types of plots, because I will have to use these plots in every single notebook, so I'll keep creating the graphs in here. So x equal to 0 to 10, y equal to x dot raised to 2, x square, and plot x comma y. Then we need x label equal to x value, then y label equal to y value. And what else do we need? We have x label, y label, then we can have one entire graph level, but let me just first run this to see what is going to happen. So this plot will not work if we did not have the plots module, plots.jl, and this should ideally not take much time. So I'm already running it, and it should take 5 seconds perhaps. Okay, so here we have the plot. We have x value on x-axis, y value label on y-axis. And it's going from, y-axis is going from 0 to 100. So here, in fact, I can change this from -5 to 5. And then run this to get the actual. Let's zoom out a little bit. So this is the y equal to x square graph. And one thing we can do here is make the graph a little bit more continuous, because here we are jumping in steps of 1. We can jump in steps of 0.01, or rather 0.1. So it will be -5, -4.9, -4.8, etc. So we'll have more number of values and the graphs will look continuous, right? This is a very simple xy plot of y equal to x square function. We can add a title for the graph, y equal to x square plot. Then we can add label equal to y equal to x square. So here, if label was not added, what would happen is, let's remove this label. Here, this will simply show y1. And if label is added, the legend, this is the sort of like a legend, it will become whatever you add here. So here you can put y equal to x square, or simply you can write, oh, I guess I'm missing a closing double quote, and this title is the overall graph title. Label is basically the whatever the plot is, right? So this is a simple plotting using the plots.jl. Just to give a starting, we will do a bit more complex plotting. Now let's explore a few different types of plots. So what we discussed in the beginning of the lecture is, let's look at line plot and scatter plot. So line plot, as you know, it will appear like something like this, discrete set of lines. Scatter plot will be simply bunch of dots, and these are all very popular type of plots that you will use in data science. So in line plot, we are plotting where x is ranging from 1 to 10 and y is set of random values of 10. So you can define x and y separately, or you can directly input the arguments here. So here you're directly inputting the x and y argument. You're defining title and you're defining label, and by default this plot will be a line plot, as we just saw in the y equal to x square plot. So what I'm going to do is, just for the sake of neatness, I will add a markdown thing here saying introduction to plots.jl and run this so that this will become like a text. And here also I want to add a title saying plots.jl package, and this is not a code, this is markdown, and run that. Okay, so that is done. Now what else? We have to get to the first line plot. So first this will be line plot, markdown, and run. And here actually I don't want to define the variables x, y either. So maybe instead what I can simply do is x will go from 1 to 10 and y will be random value from 1 to 10, random 10 values. Then x label equal to x and y label equal to y, and then title equal to line plot example. Let's not add the legend, and this is a line plot example, and whatever x label we have added here, we can put x and y here like this also, and whatever we add here will come here. And the random values, you can see that they are all between 0 and 1. So if we put something like let's see, if we put 12, I guess you have 10 x values and 12 y values. It should probably, I don't know how exactly it is supposed to plot, because for 2 values there won't be corresponding x values. I haven't tried this in the recent times, so that's why I'm not sure what happens if we put rand of 12 here instead of rand of 10. Probably it should throw an error, or maybe it should take the first few values. Let's see. Okay, Julia is idle. Basically nothing was happening, so I reverted back to 10. It's working now. So here this is random values of 10. I assume it prints only between 0 and 1. So I can test it. Print random 100 values between 0 and 1. I guess it should show 100 element vector. Yeah, all of them are basically between 0 and 1. Oh, okay, so this is fine. So this is a very simple example of a line plot. Now the next one is scatter plot. Here scatter plot means you will not have continuous line connecting between the dots, and all we need to do is like change the plot to scatter. So here you can see that it is scatter. X is still 1 to 10. Here it's rand of 10, meaning 10 random values. Title is scatter plot, x label, y label, and label. So here also we can add a label. We can add something like line perhaps, right? So label equal to, label is the argument equal to line. And when you run this, that legend will come. And then now we can run same thing with a different set of random values, scatter 1 to 10. So what I can do is here I will define a variable called let's say y1. Y1 is equal to random 10 values, right? And then here I will put y1 as the y value. So this is the line plot. Now when we plot scatter plot, it will be exactly same as this line plot, except the points will not be connected by the line. So scatter plot example, and then here instead of line we can write points. See, it's exactly same as line plot. So if you were to draw lines connecting these points, that is exactly what this line plot is. If those lines are absent, it's a scatter plot. Fairly simple, right? Okay, so just let us add a title. Scatter plot example. These are fairly straightforward data visualization fundamentals, which very likely you will be familiar with, but I nevertheless wanted to cover this for the sake of comprehensiveness. I did not want to skip anything. So that's why, and I also enjoy visualizing data in various different forms. So I enjoy making these plots. The third and fourth types of plots are bar plots and pie chart. So in bar plot, you have something like this, right? You can have things are not necessarily numbers in bar plot on the x-axis. So here it can be cat, dog, and something else, let's say flower. You can have whatever you want in the label, and then here you'll have bars signifying some values, and in the label, in the legend, you can mention what each bar, what these bars are representing. So here you can see it's bar, and then the x values are, it's an array like this. Y values are another set of array which are numbers. So y axis has to be numbers, and title is bar chart, x label and y label. Fairly straightforward. So let me write here bar chart example, and this is a markdown. Run that. Now what I'll do is I'll copy this part, and this will be bar, and here what we could do is 1 to 10. Instead of 1 to 10, maybe this could be 1 to 3. So 1, 2, 3, and actually this should be y values. X values can be non-integers, right? So I'll put this as the y, and x could be, let's say, cat, dog, flower. Then bar plot example, x label is simply x, y label is simply y, and the legends is basically bars, bar plot example and bars. You see? So cat, dog and flower, these are simply bars. So this is an example of bar plot. Really beautiful plots actually. If you include good looking plots like this in your paper, let's say you are working on a research paper, the number one thing which reviewers and editors of a journal will look at, even for conference submission, is the beauty of your plots. And there are so many customizations that you can do here in these plots to make it very, very good looking. It's already very good looking. I really like the style of these plots. It's very elegant. But there are so many things you can do, like increase the font size of the x-axis ticks and y-axis ticks, change the color of the bars, etc. We'll come to that when we come to advanced plotting techniques. The second type of plot is pie chart. In pie chart, what you have here is pi, right? You're calling the function pi, and again the value, let's say sort of like key value pair. So here you're mapping. Basically, what's a pie diagram? In a pie diagram, you will have a bunch of things. And this could be, let's say, energy expenditure based on different sector. This could be transportation. This could be household. This could be industry, whatever. So you have these are like keys, and value is whatever this is. Like if this is 30%, whatever this number is 30%. Of course, the pie size is not 30% here, but I hope you get the idea. So this is more like 15%. So you are basically having a collection of keys, and those keys are mapped with its corresponding values. So these are the keys here: Setosa, Versicolor, and Virginica. These are actually flower names from iris flower dataset, which you will see again in some time. And the values are 50, 50, and 50. So the pie chart will be equally divided. These are values, so pi percentage will be 33%, 33%, and 33%. So let's plot that. So I want to create a markdown. Let's copy this. Pie chart example, convert to markdown and run this. And pie, cat, dog, and flower. Maybe it could be, this could be human. And pie chart example. And the values could be, let's say, number of legs that these animals have. Humans 2, dogs have 4, flowers they have 0. So maybe let's say centipede. I don't know how many legs centipede has. 15 and 191. Okay, excellent. So maybe I'll write 15 here. Then instead of X label and Y label, I guess we should use different things, but we'll come to that. Let me remove those labels for now. Let's just keep the title and run this. So here you have pie chart. So centipede has maximum number of legs. So 15 out of, so totally there are 15 plus 4, 19 plus 2, 21. So 15 out of 21 belongs to centipede. 2 out of 21, which is 1/10, belongs to human, which is what you see here. And remaining 4 out of 21 belongs to dog. So here in this pie chart, it represents 21 legs, out of which centipede is taking 15, human is taking 2, and dog is taking 4. This is an example of a pie chart. And I guess we don't have to add the x-axis, y-axis, etc., because there are no x and y-axis. So you just need to add the title. It's very beautiful, actually. I absolutely love plots that look like this. You can, of course, change the color. You can change the font family of the title, etc. But let's do that in the later part of this lecture. Now, let's move on to the next chart type, histogram and density plot. Histogram, as you know, if you have a collection of numbers, let's say 1, 2, 41, 3, 1, 1, etc., etc., etc. Histogram shows you in different buckets which numbers are occurring most frequently in this list. So let's say, for example, 3 is occurring 15 times. So then this will be 15 and this will be 3. Let's say 2 is occurring only 1 times. Then this will be 2 and the height corresponding to this will be 1. But height corresponding to this will be 15. And then let's say 41 is appearing, let's say 4 times. Then this will be something like this. This will be 4, height will be 4, etc. So this is what is histogram. So here, as you would have guessed, the function name is histogram. We are creating random numbers, 1000 numbers. And out of those 1000 numbers, we are creating 30 bins. So you will have 30 buckets into which you are grouping, and you will be counting how many numbers belong to each bucket. And then, as usual, you have title, X label, Y label, right? So the only difference now is bin and the rand_n function, and we'll see what the rand_n function is going to do. So this is histogram example. Convert this into markdown and run the code. Then histogram. Okay, before that, let's do this. Rand_n of 10. So when we run rand_n of 10, you can see that the values that are created are part of a normal distribution. And how do you know that? You will know that when you plot this. So let's plot histogram rand_n, normal random distribution of 1000 numbers, bins equal to 30. Let's say that's it. I am not adding X and Y label right now. Let's just plot it. And when you plot, you can see that this is like a normal distribution centered around 0. I'm curious what's the standard deviation of this, but maybe we can explore that later. Then X label equal to X value. then y label equal to y value, and what else? Title equal to histogram. So this is exactly what a normal distribution looks like. We can keep this 10,000, and instead of 30 bins, how about we have 300 bins? What will happen? See, it's much more refined now. So this is like a very, very nice normal distribution centered around 0, going on to both sides. I absolutely like the graph style of the graph. If there are more number of bins, you will see much more discrete distribution. And if the bins are same as the number, so for example, if this is 100 and the number of bins are also 1000, then you will see that every single number is represented by one line. So each line will represent one value. And in fact, that is not necessarily true, right? Because you could have, what if you have 1000 bins? Yeah, you see, there are 1000 bins here. And if there are 10 bins, it will be better, because you are not sure if every bin will, if you put 100, if you are creating 100 random numbers and 100 bins, you are not sure there will be if there will be a number in every single bin, because you are creating bins based on the range of values. You are dividing the range of value into 100 bins. So, okay, anyways, let me go back to 1000 random numbers and maybe 20 bins or something like that. If it is 50, it will look slightly better looking, I think. Yeah, I would prefer this. So this is an example of a beautiful looking histogram. All right, now what next? We have a density plot. So density plot is very commonly used for creating probability density functions. So probability density is like, so if you have like a normal distribution, right, it's basically a probability density. And why is it called density? Because it's continuous. Sometimes these kinds of plots, which are bar plots, are called probability mass function, PMF. Mass, because when you sum up, not in this particular context, but in general, if it's a probability distribution, if they are in bars, if you add up all those, you will get 1. But if it's a probability density function, which is PDF, then you have to integrate. The area under the curve will be 1, right? So that is called probability density plot. But here it's simply density plot, which means instead of like a discrete set of bins or buckets or bars, it will be continuous plots. So here we have to use this package called statsplot. So density plotting capability will be added by statsplot. And here you can see that the only difference is, of course, we are calling the density function. We are defining 1000 random numbers, but we are not defining the number of bins, because it's a density plot. There are no bins, like it's one single continuous plot. So we can have a look at that. So let us define our density plot example, and this is a markdown, and I'll copy this code using statsplots, histogram, not histogram, density. We don't need the bins, everything else can remain. X value, Y value, title will be density plot. Okay, so this is what the density plot looks like. And why is that not like looking like a smooth Gaussian? Because we are only printing 1000 random values. If we had 10,000, this will look even more smoother, hopefully. And if we had even more, let's say 50,000, it can hopefully look even more smooth. If we had 100,000, it will look even more smooth. And when the number becomes so large, this will look like a perfect Gaussian curve. So this is an example of a density plot. I'll keep 1000 points just for the sake of plotting right now. And here you can see that it's essentially, this density plot is plotting something very similar to this, something very similar to histogram. The only thing is, on the y-axis of histogram, it's plotting the number of occurrences, right? So here you have 80 times this number close to 0 or close to, let's say 0.1 or something like that. It's occurring in that particular bin. That number is occurring or the set of numbers between, let's say 0 to, I think you have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 bins between 0 and 2, which means each bin is like a length of 0.2. So this is a bin from 0 to 0.2. So in that bin, there are 80 plus numbers occurring. That's what it means. In this bin, which is from minus 0.2 to 0, there are 80 times 80 numbers numbers between those two values are occurring 80 times. And same from 0.2 to 0.4, the numbers in that bin are occurring 80 times. So that's what this means. But on the other hand, here it's just density. It's a relative occurrence. If you normalize this by the total number of numbers you have, you will have this kind of a plot. And of course, it will not be in bins. It will be as a continuous straight line. Not straight line, continuous curved line. So this is the density plot. Now there are two plots, heat map and contour. Heat map is something I'm pretty sure you would have seen. Heat map is something like if you want to plot correlation between two variables. So let's say variable 1 takes these values, variable 2 takes these values. Then you can create a heat map that looks like this. It will be squares, and the color inside the square, the intensity of the color inside the square will decide the correlation between this variable and this variable. And there will be like a color bar also here. So that is the heat map. And here you can see that we are creating a heat map using random numbers, 10 by 10. So there are 10 random numbers correlated with another set of 10 random numbers. And we have heat map example as a title, X label and Y label, right? So these are the first set of 10 random numbers are x-axis, second set of 10 random numbers are corresponding to y-axis. So let us create that heat map example. Markdown heat map. We need random numbers, rand of 10, 10, and let's not put X label or Y label right now. Let's just see how this looks. I don't think labels are mandatory. Okay, so this is the heat map. So when you print this random numbers, right, it's like a 10 by 10 matrix. So it's directly showing the correlation matrix itself. So correlation between two values. So it could be 10 features of one particular, let's say one particular component. So if you have two animals, cat and dog, we are probably comparing 10 features of cat with 10 features of dog. It could be like that. You can use the heat map for showing the correlation between a set of variables. So if you have 10 variables corresponding to one category and 10 variables corresponding to another category, you have correlation between variable 1 of first category and variable 1 of second category, variable 1 of first category and variable 2 of second category. Like that, you have each variable you can correlate with 10 other variables in the other category. So there are 10 by 10 numbers, correlation values associated with. So that is why here you have 100. It's a matrix of 10 by 10, but basically 100 numbers. So that is this matrix. So this is the heat map. You can also add X label and Y label here. So let's add that. X label equal to X values and Y label equal to Y values. And when we run this, we have X values here. We can maybe change this to something else. Features of item 1, features of item 2. So because you have two items, you're trying to plot the correlation between the features of item 1 with that of features of item 2, and you have 10 features in each item here. All right. So now we can move on to the next type of plot, and that is contour plot. I really like contour plot because if you have worked in, let's say, electrostatics or fluid mechanics and many other physical phenomenon related fields, you would come across contour plot. So in contour plot, you are essentially plotting something in 3D, but you won't see the third dimension. You are plotting contours of some equal values. So here you have x values first, right? So x value is defined from -5 to +5 in steps of 0.1. Y values are defined from again -5 to +5 into steps of 0.1. And z is sine of square root of x square plus y square for xi in x and for yi in y. And then you are plotting contour, and here you need 3 arguments because there are 3 axes, x, y, z axis, but it will look like 2D only. It will not look like 3D. I'll show you. And then the title is contour plot, x label, y label, right? So let's code this. So contour plot example. This is the markdown, and let's run this. So first x equal to, in fact, I'll name this as xc because x contour. I think I have used x variable somewhere in the above plot. This will be from -5 to 0.1 to +5. Then y contour equal to -5 to 0.1 in steps of 0.1 to +5, and z contour equal to maybe sine of let's say x value square plus y value square for x value in xc, I don't know if and y value in yc. I'm pretty sure the syntax is not exactly right, which is why we can check back. Sine of that for x in this and y in this, and you need a square bracket, obviously, comma y value, and contour of x contour, y contour, and z contour. I'm not going to specify axis or anything right now. Let's just see if the syntax, everything is fine here. Contour is not defined in main, and that is because check for spelling errors. Oh, I have a spelling error. Yeah. Okay, so this is the contour plot, and here see what we are plotting. We are plotting sine of x value square plus y value square. And do you see this region of constant color? So x square plus y square is basically the equation of something that looks like a circle. So for example, let's go here. If x square plus y square has to be constant, it's basically a circle that will look like this, because if this is 1 and this is 1, x square plus y square is 1 here, x square plus y square is 1 here, it is 1 here, it's 1 here, it's 1 here. So basically, if x square plus y square has to be constant, then sine of x square plus y square will also be a constant value. So the contours will be bunch of circles. Now you might be wondering, why exactly are these circles looking like ellipses? That I would say is because here it has been a little bit elongated, I would say, because to my eyes these look a little bit like ellipse, but if you look at the value, this is from -2.5 to +2.5, and this is from +2.5 to -2.5. So it is supposed to be circle, but it's, to my eyes, it's for some reason appearing like a little bit like ellipse, probably because of some, I don't know, squishing, or am I making a mistake here? Y value square, x value square. We'll see that. Maybe if we make this into 0.01 and plot, we can see how the color has changed, because now we have more number of values. All right, this definitely looks ellipse to my eyes. Anyways, now one more thing is, do you know why this color is repeating? Because sine can only go from -1 to 1, right? So the values are -1 to +1, and that's the reason why you can see repeating values here. But what if this was simply x square plus y square, sine was not there? Then the color cannot repeat. Color will go from, the values will go from 0 till 25. So when x, see, these are like circles. This is actually circle, although it may not appear like that. I think this is not the scale of x-axis and y-axis is probably slightly different. But in any case, the value will go from, so x value square plus y value square, the least value that it can take is 0. The maximum value that it can take is x square is 25, because 5 square is 25, minus 5 square is also 25, y square is also 25 maximum. So 25 plus 25, it will go maximum till 50. And where can that happen? 50 can happen when x and y both are 5 or -5, or one is -5 and other is 5. So basically all these four corners. So these corners should have the highest value, as you can see here. Now, you can of course put label x label equal to x values, y label equal to y values, and title equal to contour plot. So this should add some beautiful looking labels. Fine. So this is about contour plot. I don't think we are trying anything fancy yet. Fairly straightforward. Maybe you can try something like something that can actually make this look like an ellipse. What if we add a 3 here? 3 times x value square. Then this will definitely not look like a circle. Now this is an actual ellipse. See? And if you want to elongate ellipse in the other direction, in the y direction, you just simply add 5 times y value square here. Then it will look like a ellipse elongated along that direction. Now it's an actual ellipse. Previously it was a circle. And what if I do not have a square here? Then what will happen? Then this will be like a parabola, set of parabolas, because this is like a quadratic equation. And what if I don't have square here as well? It's like a straight line. So there will be a bunch of straight lines through which values are constant, right? This is the contour plot. Basically, these lines are lines where values are constant. So this yellow line has a constant value for the Z. So ZC, you're not plotting in 3D, but through the color, you are trying to express the value of ZC. So value of ZC is 10 if the color is kind of yellow. Not this, I would say 10 is probably in this corner, but this guy is probably 7.5 or maybe something between 7.5 and 10. And here it's -10 at this end. Okay, so that's it for the contour plot. I think now we can move on to the next type of plot. So there are group bar charts, box plots. I really like box plots. Group bar chart is also interesting, but probably not as highly used as these box plots. And then the last one is 3D plot before we go into an actual data science visualization. So group bar chart is nothing but you can create, see here you have two groups, label group 1 and group 2. And I just want to show you how this group bar plot looks, right? So these are the keys. So corresponding to A, you have 3 values, 5, 8, and 2. Corresponding to B, you have 3 values, 7, 3, and 6. And you have 2 groups. So without adding any group title or anything, the function name is, by the way, bar. So that does not change. So grouped bar plot and markdown. So the best way to learn this is you open the Jupyter notebook yourself and try coding along with me. So that way you don't have to just watch me code, you can code along with. That is the best way to learn this particular lecture. But as you wish, you can skip from one plotting style to another, and if you want to, code after you are done watching the lecture, that's also fine. So bar of we need first two groups, right? So maybe the first group can be called as A, and the key of the second group is B, and we have three numbers associated with first group, and that will be, I guess, 1, 2, 3. I'm not sure if the syntax is perfectly correct. 4, 5, 6. I just want to check my syntax over here. I don't think, okay, it's separated by a semicolon. So I guess comma is fine, but then they have to be separated by a semicolon. If comma has an issue, then I'll remove the comma and just put space. But let's see. Unexpected semicolon in array expression. How about this? Okay, so this is how we are plotting. Now you might be wondering, why is this appearing like this? You don't see any groups. Where are the groups? So the problem here is, when you put so here you have three numbers in group A and three numbers in group B, right? And what is happening here is, first it's plotting. I'll show you what's happening. Just let me switch the order. So instead of 1, 2, 3, let me write 2, 3, 1. Sorry, 3, 2, 1. 3, 2, 1. And instead of 4, 5, 6, I'll write 6, 5, 4, so that the biggest number comes in the beginning in each group. So now you can see that, so in the first group, you have three numbers, 3, 2, and 1. So now this is plotted in such a way that in the first group, the tallest bar has a height of 3. The second tallest has a height of 2. The third tallest has a height of 1. So you're plotting it such that the tallest one is behind. The shorter one is ahead of it. The shortest one is at the front. But if this order is flipped, you will only see this tallest bar. You will not see the other bars. So that's the reason why you have to plot the biggest number in the beginning. Now, for example, if you switch 1 and 2 here, what's going to happen is, now 2 will be, 3 will be at the back side. Then 1 will be next, then 2 will come, which means you will not see 1 now. If I run this code now, you will not see 1. So 1 disappeared, right? Whereas if you plot it like this, now it's fine. Now the question is, what are the labels actually? In every group, you have three values. Maybe the labels are label equal to, let's say, feature 1, feature 2, and feature 3. It could be three features. I hope the unterminated string is there, because, yeah. So this could be three features. Oh, I should not have. Basically, I want to say that feature 1, feature 2, feature 3 is not working. What if I simply put this? Right. Okay, just put a space and then write feature 3. Okay, perfect. So now this could be, let's say, person 1, person 2, and let's say there are 3 subjects, right? Maybe we can say something like, let's say there are 3 subjects: physics, chemistry, maths. Chemistry and maths. And we are plotting there are 2 people, and we are plotting the scores in physics, chemistry, and maths for these people. What would be ideal is, instead of plotting one behind the other, if these are plotted side by side. So let's see how to do that. So actually, I checked a little bit and I realized that to plot a group bar plot, the better function is not bar, it's called group bar. But if you try to run this, you will have to use this package. You will have to run using stats plots. If you don't import this package, this will not run. But basically, see, right now this is much better because here you have two people and you can have labels, right? So let's say our labels are marks in some exams. So let's say first is physics and chemistry, and you don't need this, you just need a space bar. So math, and see, so blue corresponds to physics. So you can see that person one is scoring, and here, in fact, it does not matter. The order only corresponds to the subject. So if the first one is physics, you can put whatever number. The scoring could be lesser in physics and higher in maths, does not matter. So if this is out of 10, you can, the order does not matter because the bars are not coming one in front of the other. So the issue of one bar kind of hiding the other one is not occurring. So this is the perfect example of plotting a very good bar plot, a group bar plot. So here there are two groups. One group is for person one, another group is for person two. And in each group, there are three items. So here in the first group, there is physics, chemistry, and math. In the second group also same, right? So this is an example of group bar plot. So what I have done is here also I have changed in this code also, I have added like using stats plot and group bar. All right. Now let's look at box plots. So box plot is another very interesting plots. I am sure you will come across this in plenty of data science related problem statements. So I just want to give you a basic idea. So here, the data that you are plotting in this box plot is nothing but a set of random normalized numbers, random numbers, 50 of them are there. And then you are adding a number between 1 to 5 to that. So let's see, right? Let's go to Julia, and then you are just plotting box plot of data. So box plot example, and we can convert to markdown and then just run this. And data equal to of 50 plus I for I in 1 to 5. I think we have to add dot, and box of data, I guess it's in box plot. All right, so this is the box plot. So see what we are doing here. Here you have 5 boxes, and in each box, so here what's happening is I runs from 1 to 5, right? So when I equal to 1, a set of random numbers whose normal distribution is such that it is centered around 0 is added to 1. So basically it will be a set of numbers which will be maybe 1 plus something, 1 minus something, etc., etc. So mean value will be somewhere around 1. When I becomes 2, that will be 2 plus set of random numbers from minus something to plus something. So the mean value will be close to 2. So that's what this plot is showing. So there are basically 5 set of numbers, 5 set of 50 numbers. And how do we know that? We can actually plot data. I mean, print data. So just print data, 5 element vector, and each vector you can see that each vector will be of a particular dimension. Data.size is 5. Maybe I can print data of 1. This is 50. So 5 multiplied by 50. Each set has 50 numbers, and like that there are 5 sets. And the mean value of the first set is close to 1. It's not exactly 1 because you are adding random numbers. Mean value of second set is close to 2, close to 3, close to 4, close to 5. And there will be a standard deviation. So for some of these sets, you see these dots. That's because the range of numbers that are generated is exceeding that deviation. So this is deviation to the plus and deviation to the minus. So it's called as lower and upper quartile. So this is upper quartile and lower quartile, and whatever you see outside of that are outliers. So here, instead of this, if we plot, let's say 150, you will see more number of points being generated. And if you run this again and again, this will change, because see, sometimes the outliers will be present in the first two sets, not in the next few sets. And you can do this, you can run this, and the outlier generated will depend on the data set. But basically this is box plot, and it's very, very good looking. X label equal to, let's say, let's say experimental data, and let's say 1, 2, 3, 4, 5 is experiment number. So maybe then I can rename this as experiment number, and Y label equal to maybe temperature. I'm just saying something, temperature. And here I can say this is from 271 Kelvin to 276, something like that. And then you see this is like 5 different experiments, and you have temperature. You can also kind of do something like a random, let's say each experiment has like a different temperature, 230, 325, and 440. Then you will see different type of plots. And now if you reduce this from 440 to, let's say, 300, the plot will look slightly better. And this can be, instead of 230, if this is 290, slightly better. So this is the box plot, right? So if the range of Y values is very high, the box plot will kind of, you will feel like the box plot shape is changing. But it's essentially a box plot when you look at individual boxes separately. Then what else did we need? A label. So here we can put labels like experiment 1, then experiment 2, and let me copy paste. Then this is 3, sorry, this is 3, this is 4, and this is 5. And since we have only 5 experiments, I can delete this, and the legends also changed accordingly. Now we can do one more thing, right? So here, if I delete one of these, then number of experiments will reduce from 5 to 4. Then I can delete the last 5th experiment. And when we plot this, you will see that there are only 4 bar plots. And let me change this to 280. Not bar plot, box plots. I meant to say box plots. These are beautiful plots. If you ever worked in any kind of experimental setup, these are very routinely encountered. Okay, so with box plots, now we can move on to 3D plots. I absolutely love these plots. So this is another version of the contour plot, except here you actually see things in 3D. So X is running from 1 to 10. Y is running from 1 to 10 as well. And here Z is defined as X times Y. And this is like a surface plot. So that's why this is a 3D plot. And X, Y, Z. So very similar to contour plot, right? So let's go here and let's say 3D surface plot. And this is a markdown. So we can run this like this. And okay, so X 3D equal to minus 5, 0.1 times plus 5. Y 3D equal to same, minus 5 to plus 5. And let's say Z 3D equal to X 3D square. X 3D value, actually X value square plus Y value square for X value in X 3D, comma Y value in Y 3D. And then here I can simply plot surface of X 3D Y3D and Z3D. This should hopefully work, assuming all the syntax is fine. So x square plus y square means it will be like a parabolic vessel shape. So z equal to x square plus y square from -5 to +5. So z values can only be positive because you are squaring, and its shape should be such that when x equal to 0, y equal to 0, it's minimum. So that's what we are plotting here. Attempted to save. Okay, I guess there is some kind of syntax issue. Let's see. X value square plus y value square for this is, let me check the syntax once. Surface xyz, everything looks fine. X value, I'm not sure what is going on here. Let's see. Let's just keep it like this. Okay, so this is working, but what if we add 0.1 as the range? Is there an issue there? Okay, it's working. I don't know why it did not run previously. And this is an actual 3D plot. You can visualize the graph. So this is x value square plus y value square. And if we put a sine of this, then basically it will be a sinusoidal wave whose value will repeat along circles. So you remember the contour plot which we had plotted above like this. So in the contour plot, where is that? Yeah, in this contour plot, when we plotted sine of x value square plus y value square, basically along circles, the value was repeating, right? 0.01. Okay, I think here there are so many x and y points. That's why it's taking some time to run. But basically, you see, you had something like this as the contour. Now, if this is plotted in 3D, you should see something similar. But now this time you can see what's the exact same thing in 3D. So -5 to 5 sine of x square plus y square. Let's plot this. It should look like wavy patterns, symmetric along any direction, any radial direction. So see, this is that. I guess the reason why it looks a little bit choppy at the edges is because this if we make it a bit finer, it will not look that choppy. See, now it's much more beautiful looking. So this is very, very cool. I absolutely love this plot. We can, as usual, add x label equal to x value, and let me copy paste y label and z label equal to y value and z label equal to z value. So it should have, there are 3 axes here, right? So I think there is an extra comma. Okay, so there are 3 labels and 3 axes. Very beautiful, very, very beautiful. I absolutely love this visual appeal. So these are 3D surface plots. Now this plot is exactly same as this plot, except in this plot you are looking from the top to down along the z-axis. Here you are directly plotting it in 3D. And here the colors are chosen such that same values will have same colors. See the color bar here. Same here actually. If you look at this color bar, same locations with same z value should have same color. So if you take a slice along the z-axis, wherever that slice is intersecting this surface, there should be the same color. So this is 3D surface plot. Now let's come to the last thing, a data science use case. So here, this is like a plotting of iris dataset. Iris dataset is very famous. I just want to check after the iris dataset. Yeah, this is a minor adjustments are remaining, but basically iris dataset will be very close to the end of this lecture. So what we are doing here is we are loading the iris dataset. I will show you what this dataset exactly is using the csv.read function. Now this csv.read function is something that we had introduced in one of our previous lectures, but basically it's a function which allows you to read a CSV file from your local or from your internet. Then this renaming, I'll show you what exactly is being done here. And then here we are plotting a scatter plot. And there are 3 groups, setosa, versicolor, and virginica, right? So basically, it's a simple scatter plot of the data. So before running any of this, let me actually show you the data set, how it looks like. So let's open this link. So this is how the data set looked like, right? So it has sepal, it has actually 1, 2, 3, 4 sepal length and width, petal length and width, and finally the category iris setosa, iris versicolor, and iris virginica, right? So what we can do is we can actually save this as a CSV file. So instead of .txt, we can just save this as CSV, iris data.csv, and then let's open this. And here you can see that, not this, here you can see that this is how the CSV file looks like. Now the only issue here is like it does not have a header, so we can add a header. Maybe to add the header, it's easier if I just open this as a txt file. So let me do that. So here I have opened the same file as a txt file using text editor, and we have these 5 values. So I'm just copying sepal length, sepal width, petal length, petal width, and then the species. So let's go here and text editor, and I will paste it here. Now what we have to do is remove these. So we don't need the double quotes. It's not necessary. So now this can act as the header, right? Okay, iris underscore data dot CSV. So I'm directly editing CSV using the text editor here. Okay, it's comma separated. Let's close this. Now what we can do here is in the code, let's come down using data frame and CSV, CSV.read, and we need to mention the path here. So path is actually in my download. So I just downloaded this, right? So in downloads, there should be like a iris data.csv somewhere. Let's see, where is that? Iris data.csv. This is the one. So then here click copy path and then put it here. So csv.read. This is the, okay, we are not yet to put it as data frame, but package data frame is not found. How about data frames? Okay, so data frames, downloads, character literal contains multiple character. So what am I missing? I'm missing csv.read. Yeah, header equal to, it's not false. I need header. Okay, double quotes. Data frame. Then I'll name this as iris data frame, iris df equal to csv.read this. Header equal to false, I will remove. And hopefully this should read. Not a valid file. That is because let me see what is the present working directory. Okay, I have to. I'm in downloads only. So I guess maybe I don't need this. I simply need to mention the CSV file because I guess I'm already in the downloads folder. Okay, fine. Correct. So I was already in the downloads folder. So that's why PWD present working directory showed downloads. So we are reading the CSV file, right? So then what should we do? Iris df.head. We can just print the head not found in the data frame. We should put probably header equal to false. I don't know. Okay, iris dot head is not found, but iris df is there. So now what are we plotting? We are plotting sepal length and sepal width probably. So scatter plot of sepal length versus sepal width. And there should be three categories. Iris df dot sepal length, iris df dot sepal width. Now, why are the three categories not forming here? The reason why scatter plot is not creating three separate categories is because we have not done grouping. So group equal to, we need similar color for similar plots, iris df dot species. Because see, the header name is of the last column is called species. This one, iris setosa, iris virginica. So that's why we need iris df dot species. And see, now it is very nicely categorized. So then we can write x label equal to, I think one is sepal length, right? X is sepal length. Then y label equal to sepal width. All right. So now you have sepal length plotted against sepal width for three different categories. These blue dots in the scatter plot are all iris setosa. This red/orange are all iris versicolor, and the green one is iris virginica. So this is amazing. This is exactly directly taken from a data science project. So this iris dataset is basically, these are flowers. Iris, I'm sure many of you are probably familiar with this. Basically in the iris dataset, there are flowers which look like this, and its smaller ones are called petals and bigger ones are called sepals, and they have length and width, and based on the length and width, you can classify these flowers. Now, a classic machine learning problem here is like building a any kind of ML model that can make a prediction whether a new flower is a setosa or versicolor or virginica based on its sepal length or sepal width or petal length or petal width, right? So that was this. So this is an actual data science project that you just implemented in this piece of code. Now let's move on to the last part. Last part is little bit customization, adding grids or themes, layout adjustment. So here, let's see what we are doing here, right? So this is like a, if it's simply plot, it means it should be a line plot, right? As we saw. So line plot, there are random 10 numbers. We are adding title, we are adding X label, Y label. We have seen this much already. Here we are mentioning the title font size, guide font size, tick font size, background color light gray. We are mentioning grid and we are mentioning legend. Legend you have already seen, but basically it's just the location of the legend. You remember the label that we had added, the name of the label was appearing in the legend, but we were not controlling where the legend should appear. So we will control that also here. So what I'll do is, like, for convenience, let me simply copy this. This is a very simple piece of code. No need to write it from scratch. So I forgot to add the markdown corresponding to this, but that's okay. So here, if we are plotting, see, this is a style, this is a bunch of things here we already know. We are plotting random 10 numbers. It is a line plot. If we convert this into scatter, it will become a scatter plot, right? Okay. But let's keep it as line plot for now. Random 10 numbers. Title is the title of the graph. This X label, Y label basically forms the text that forms here and here. But that we already know. Now legend, it has few different locations. So right now it's at top, which means it's right here. How about this top left? Then it will move to top left. So you can define top left, top right, bottom left, bottom right. Bottom left means it will be here, obviously, and bottom right will be here, and top right will be top right. Okay. Okay. So then title font size, here you can maybe increase the font size like this, fairly simple. Guide font size, let's say we increase this, then the labels font size is doubled. So these two things are guiding you. tick font size is, these are ticks, right? So if we make this 20, the individual ticks are increasing in size, but this is looking very ugly right now. So I'll go back to whatever it was before. The default ones were actually much better. The last thing is, okay, grid, maybe what are the options in grid? I don't know if line actually works. Yeah, line does not work. Dash, Julia, line, plot, grid, options, changing grid. So you can actually read in this, make something into plots. We'll come back to that. I don't think this is, I was just checking. Background color, light gray. What if we make this black? Then, okay, you see something cool that happened. So basically, when we initially, when this was, let's say, white, then the font color is black. The lines are black. Title is black. This is blue, right? But now if the background color itself is black, you see the font is switching. This black has become white. Whatever was black has now become white. So the legibility, the readability of the graph is not compromised. So this is very, very good. I absolutely love this. Similarly, if you convert this into yellow, all the things should become a bit darker. There are many different colors you can define. And of course, you can define it in any other way also. But what if we define blue? Okay, what if this is light blue? I don't know if such a color exists. Okay, all those colors exist. Red. So you can pick whatever is not looking hideous. I really like the elegance of this black plot. It's very simple and it looks pleasing to the eye. But this won't be part of research paper. So if you're making figures as part of the paper, it should be white background ideally. You don't need the grid lines. So if you don't need the grid lines, just remove it. What happens if I put none? Okay, grid is gone. Excellent. So if you don't want grid, what if we put y grid? Okay, if y grid is none, it means grid lines along the y-axis will be gone. But if this is x grid equal to none, then only these lines will be there. These won't be there, right? Very, very good. So this is the customization part. So I think we are at a good place to summarize today's lecture. It's been a bit long lecture, I know. But data visualization is one of the most important aspects of, I would say, data science. Even when you're building machine learning models, writing papers, or making dashboards for your customer, at the end of the day, you have to be able to tell the story in the form of data. And most of the storytelling will happen through graphs and plots. And that's exactly what we covered. We looked at line charts. We looked at, so this was like a line plot of an equation. This was a random line plot, scatter plot, bar plot, pie diagram, histogram, density plot. This was correlation heat map. This was contour plot. We saw the 3D version of this also. This is group bar plot. This is the box plot. This is the 3D surface plot. Then this is the scatter plot, grouped scatter plot. And this is basically the final styling. We did some styling at the end. So I covered this lecture a bit slowly. So that's the reason why this whole lecture will be a bit longer. But I'm glad that you have reached until this stage. If you did not understand something, try this yourself. This is very, very simple piece of code. Nothing is complicated here at all. It's very, very easy. So just go through this. There are even more beautiful and more complex plotting styles. Like there are like candle plots, violin plots. There are many types of plots, and you will learn all of them as you go along in this course. So I want to take a moment to appreciate you for going through not only this lecture, which was a bit long one, but also for going through all the past lectures and reaching up until this point in the course. And the reason why I keep saying this is because it's not easy to kind of stay committed once you start something. It's not always easy. I've generally seen that the number of people who are carrying forward with their journey in the course exponentially decreases. The first lecture, there will be maximum number of people. Second lecture, it decreases. And by the time we reach the last lecture, the actual number of people who have covered all the lectures, it will be a small fraction of the number of people who started with the course in the first lecture. But if you are already at this stage where you are almost finishing up this data visualization module within data science, you have already kind of gone ahead of 99% of the people who may start the course but will never finish. So I really want to congratulate you and appreciate you for that. We will see again in the next lecture. Thank you so much and take care until then. Bye.